Okay. Section 8.1, similar polygons. Our objective for this lesson is to use similarity statements, find corresponding lengths in similar polygons, find perimeters and areas of similar polygons, and decide whether two polygons are in fact similar. So first we need to talk about what a similar figure is. If you remember from way back chapter 4 when we discussed dilations, we talked about similarity transformations. Two figures are similar if and only if, again that's a biconditional, it goes both ways, if and only if there is a similarity transformation that maps one figure onto the other. Okay. So if you can get from one figure to the other using a similarity transformation, then they are similar. Our similarity transformations were our dilations, scaling things up or down, our dilations and or a combination of them, and or a combination of dilations and rigid transformations. And our rigid transformations included our translations or slides, translations, rotations, and reflections. Okay. So if I can get from one to the other by a dilation, scaling it up, scaling it down, a dilation and then a translation, a dilation then a rotation. Again, a translation is just our slide. A rotation rotates around. We either did 90, 180, 270, and then our reflection flipping over the X or Y axis, okay, for our reflections. Okay. So when we perform one of these similarity transformations, we get what's called similar figures. Okay. So in this diagram down here, triangle ABC is similar to triangle DEF. So how we would write that is triangle ABC is similar to triangle DEF, and we have a symbol here that means similar. This little, it's called a tilde. This little tilde means is similar to. Okay, so it's basically just almost like congruent, but without the equal part. Okay, it's just the little curly mark. Okay, so here we have triangle ABC is similar to triangle DEF. Again, the order in which the points are arranged matters. This tells me that A is going to line up with D, or we say correspond to D. Okay, B is going to correspond to E, and C will correspond to F. Okay, a similarity transformation preserves angle measure. Okay. A similarity preserves angle measure, meaning two similar figures off to the side here, similar figures have congruent angles. Similar figures have congruent angles. The angle measures do not change. Similar figures have congruent angles. Okay? So all corresponding angles are congruent. So this tells me in this picture, the way these are ordered, angle A is congruent to angle D. Angle A is congruent to angle D. Then since B comes next, angle B would be congruent to angle E, B congruent to E, and then C congruent to F, because that comes last, C and F. C congruent to F. Okay. A similarity transformation also enlarges or reduces side lengths by a scale factor K. So we get back into the scale factor idea. Remember, scale factor K, scale factor is equal to image over pre-image. Okay, so you go from your image, where you end up, over your pre-image, where you started. Okay. So here, if I consider this my pre-image where I'm starting with this one, going to this one. You see the direction the arrow's going to this one. So that tells me that this one here is my image. This one here is my pre-image. So that tells me, so the corresponding side lengths are proportional. What we mean by proportional, they're ratios, meaning division. Ratios is just another word for division. The ratios of division, the ratios are equal. Okay, their ratios are equal. So if I was to take side DE and divide it by AB, because again, those are corresponding parts, DE divided by AB, okay, that would give me that scale factor K. Okay, but then it would also equal EF over BC. EF over BC. But that would also equal FD over CA, and they all equal the scale factor. They all equal our scale factor K. So we have all these ratios set up. This right here is what we call a statement of proportionality. Okay, this here is our statement of proportionality. It writes all the side lengths into appropriate ratios. So if I take DE and divide it by AB, I'm going to get K. If I take EF divided by BC, I'm going to get K. If you take FD divided by CA, I'm going to get K. So these all equal each other. So we can use that to help us solve for missing side lengths. Okay, we're going to do a little sidebar and talk about proportions for a minute. So we're going to talk about this proportion idea for a minute. A proportion, again, is saying two ratios are equal. So let's say ratio A over B. Let's say that equals C over D. So this is a proportion. A over B equals C over D. We have special names for certain parts of these proportions. The first one, the A, and the last one are what we call extremes. Okay, so the first A and the last D are what we call extremes. Okay. The other ones, let's switch colors. I don't know, let's go to green here. The B and the C, the middle ones, the B and the C are what we call the means. Okay. The B and the C are what we call the means. And what's interesting about these is if I multiply my extremes, the A and the D, multiply A times the D, multiply the extremes, so these are my extremes, they will equal the product of the means, the B times the C. This is what we call the extremes means theorem. Okay, so this is what we call the extreme means theorem. So we have extremes means, extreme means. Okay, so basically this means when I multiply the extremes, the first and the last, it's going to be equal to the product, the multiplication of the means, the middle two. Okay, and so we'll use those a lot. That's just an idea on, a lot of times extremes and means, these words aren't used very often much anymore in algebra, but they are still used in geometry, and we'll get into more extremes and means later in this chapter. Okay, just wanted to kind of review that idea a little bit. Okay, so here in example one, extra example one, this one isn't in your book. So in the diagram, they tell us triangle ABC is similar to triangle JKL. So they tell us the two are similar. They want us to find the scale factor from triangle ABC. So we're starting with triangle ABC, and we're going to triangle JKL. So they want us to find that scale factor. Again, scale factor is always image over pre-image, so it's always going to identify which is which. Well, since I'm starting with ABC, this one's my pre-image, and going to JKL, this one would be my image. So to find the scale factor, really all I need is the ratio of corresponding sides. So I pick one set of sides. I'm going to start with the first two. It goes A to B. So I'm going to go side A to B, and then JK. I'm going to just look at those orange sides there to get the scale factor. So I want to then set up, I need to take my image, divided by my pre-image. So to find my scale factor k, take my image, which would be jk, and I would divide it by my pre-image, which would be ab. Well, jk is 36, divided by my pre-image, which is 27. 36 divided by 27 is, we'd simplify that, I think 9 goes into both of them. 9 goes into there 4 times, 9 goes into here 3 times. So my scale factor is 4/3. So what that tells me is if I multiply each of these sides by 4/3, I get to its corresponding side. And we can double check it. If I take 27 times 4/3, I get the 36. 21 times 4/3, I get the 28. 36 times 4/3, I get the 48. Okay, so I multiply all of these sides by my scale factor k here, my 4/3, to get to here. Now it says, so we found the scale factor. There's my scale factor, 4/3. List all pairs of congruent angles. So now we want to match up angles. Well, that's as easy as reading the similarity statement. This guy here is what we call our similarity statement. It tells us how these are similar, which angle matches up to which angle. So this is our similarity statement. Okay. So angle A is going to go to angle, so angle A is going to be congruent to angle J. So there's a pair of angles. Angle B is going to be congruent to angle K. And then angle C is going to be congruent to angle L. Okay. And I was able to read all of that off that similarity statement. But we can see here, A is going to match up with J, B with K, C with L. Find the ratios or the corresponding side lengths write the ratios of the corresponding side lengths in a statement of proportionality. So a statement of proportionality is going to look like this. Again, image over pre-image. So we're going to go image over pre-image. So we'll go, let's start with our sides. So we'll go JK over AB. Well, that's going to equal, that's J to K. So now let's go K to L. K to L over B to C. And that's going to equal L to J over C to A. Again, we just list all the sides in proportion. And if you notice, I don't put segment lengths above these because we're talking about the division, so we're really looking at that number. Okay? And we know those should all equal 4 to 3 because that is our scale factor. J to K to A to B is 4 to 3, KL to BC would be 4 to 3, and then LJ to CA would be 4 to 3. Again, we can pull all that off of here, but we can also look at the picture and determine which sides go with which. Okay. So if two polygons are similar, then the ratio, again, that division of any two corresponding lengths in the polygon is equal to the scale factor of the similar polygon. So again, you just take the ratio of the side lengths, again, always image to pre-image, image over pre-image, and that will get you that scale factor. Okay, so in the diagram, triangle GHM, so GHM, is similar to triangle HKL. We want to find the value of x. So x is this side length right here, K to L. Hey, so which side is going to line up to side KL? If you notice, KL is his last 2 points, KL. So it's going to be the last 2 points here, HM. Well, they tell me that HM is 12. And so you can really decide here. They don't really tell you which one you start with. You start with bigger, you start with smaller. So it's up to you to decide which way you want to do it. I'm going to have the smaller one be my pre-image, and the larger one here be my image. So my image is this guy, my pre-image is this guy. So we always go image over pre-image. So I would go x over 12. Okay, but that ratio is going to equal the ratio of any of the other sides. So now I just pick 2 other sides that we know both. They give us both. Doesn't matter which sides. I think I'm going to go G to H. The first 2, G to H and H to K, because G to H is 10, H to K is 15. Again, we're doing big one And sometimes it's helpful to write which way you went. I went big over small, just to make sure you don't get those mixed up. I went big side over small side. Well, that's going to equal then big side with h to k, which is 15, over small side is g to h, 10. So now I have a proportion, and I can identify my extremes. So my extremes would be the x and the 10. So if I multiply those, x times 10, it's going to equal the product of my means. My means are the 12 and the 5. Sorry, 15. 12 and 15. So now, x times 10, that's just 10x, is going to equal 12 times 15, let's calculator that up, 180. So now I have this equation, 10x equals 180, divide both sides by the 10, x equals 18. So we found this missing side length is 18. And you can always double check them to make sure. If I divide pre-image divided by image in all of these, let's go 15 divided by 10 is 1.5. 18 divided by, it would be the 12, is 1.5. And then 27 divided by 18, 1.5. All their sides are in proportion. Okay. Here, extra example 3. In the diagram, triangle UVW, UVW, that's the smaller one, is similar to triangle QRS. QRS. Find the length of the median ST. So we're trying to find, our goal is to find the length of this median. Okay. So what's interesting about similar triangles is if two triangles are similar, okay, all their linear measurements, all their linear measures are proportional. Okay, so if two triangles are similar, then all their linear measures are proportional. And what I mean by linear measures are measures that you can measure with a straight line ruler. Okay, linear, straight line, you can measure them with a ruler. So it's that nice straight line, linear measures. Straight line, you can measure them in feet, inches. It's basically just talking about straight length. All their linear measures are proportional. And even more so, they're proportional, they're equal to the scale factor. Okay. So they're equal to the scale factor. So this median, the length of this median is a straight line measure. It's just measured in inches, centimeters, whatever, it's straight line. So that tells me it's going to be proportional to the median in the other one. So I know that the length from S to T is going to be proportional to the length of W to Z, because that's the median, that's the same median in the other triangle. Okay. So that'd be WZ. And again, we went, what did we go? We went big, bigger one to smaller one, big over small. Okay, so S to T, so let's have S to T here be my X, what we're trying to find, lowercase x. Okay, and that's going to be equal to the scale factor. So I need to determine the scale factor if we go big to small. Okay, so we're going scale factor big, so my big one here would be, well, again, we can decide whatever side we want to use. I'm going to use side QR, and I'm going to put it over VU. So QR, length from Q to R over length from V to U. Well, Q to R would 36 plus 36, so Q to R would be 72. Okay, Q to R, 36 plus 36. Okay, V to U, 16 and 16, 16 and 16 is 32. So now we can just plug in. S to T is X. W to Z is 12. Q to R is 72. V to U is 32. So now we just look at means extremes. Extremes are my X and my 32. So I take 32 times X. That's going to equal the product of my means, the 12 and the 72. So now we just multiply. 32X is going to equal 12 times 72 which is 864. Divide both sides by the 32. 27. X is equal to 27. Okay, so S to T, so find the length of median ST. S to T is 27. That would be our final answer there. Okay. All right. So that leads us to our first theorem of this chapter, the perimeters of similar polygons theorem. If two polygons are similar, then the ratio of their perimeters, perimeter, again, perimeter distance all the way around, is equal to the ratio of their corresponding side lengths, because perimeter is a straight line measure. Perimeter is a linear measure, straight line, measuring distance all the way around. So, I really don't need to know what all four sides are to actually find the perimeter, because the perimeter here, PQ plus QR plus RS plus SP, that's the perimeter of this guy. KL plus LM plus MN plus NK, that's the perimeter of this guy. The ratio of those two will be equal to, well, the ratio of just any two sides, any two sides. Any two sides being equal to that ratio. So all I need to do is know the ratio of two sides and one of the perimeters, and we can find the other. Like here in example 4. Your neighbor has decided to enlarge his garden. The garden is rectangular, so here's my original garden. Rectangular, with the width of 6 feet and a length of 15. Okay. The new garden will be similar to the original one, so we're enlarging it, but it's going to be similar, so that means we'll have that appropriate scale factor. The garden will be similar to the original one, but will have a length of 35 feet. Find the perimeter of the original garden and the enlarged garden. Well, the perimeter of the original garden, well, if this side's 6, then this side's 6. If this side's 15, then that side's 15, because opposite side's congruent, right, in a rectangle. So the perimeter of the original is 6 plus 15 plus 6 plus 15 all the way around, or 15 times 2 plus 6 times 2. The original perimeter is 42 feet. Again, linear measure, 42 feet. Okay. But the ratio of the perimeters, so this is the perimeter of the original. We'll go perimeter of O. Let's put an O down there for original. We're trying to find the perimeter sub new. Let's put a little N down, perimeter of the new one. But the ratio of these perimeters is going to be the same as the ratio of the side lengths. So we know one side length. We know this side's 15, this side's 35. So the ratio of the perimeters, perimeter new to perimeter old, is going to be the same as, again, perimeter new, that's big. We're going big to small. Will be the same as the perimeter of the side length if we go big to small, 35 to 15. But we know the perimeter of the original, that's 42. So perimeter of new to 42 equals 35 to 15. So now we just means extremes it. Extremes. So that would be 15 times perimeter new means 42 times 35. And these two are going to be equal. So 42 times 35 gets me 1470. So 15 perimeter new, divide both sides by 15. Oh, perimeter new. The new perimeter, 1470 divided by 15, 98 feet. So it says to find the perimeter of the original garden. Here's the perimeter of the original garden. Perimeter of the new garden, 98 feet. And remember, put units on it if it has units. Okay. All right, we just have one more thing to cover and then we'll end it. I know the video is getting a little long. Areas of similar polygons. Area here is not a linear measure. Okay. It is a square measure. It's measured in squares. So the ratio of the areas is equal to the squares of the ratios of the corresponding side lengths. Because if you notice, the squares. So we have to square the ratio of the side lengths to get the ratio of the areas. Okay. So here, we have to square the ratio of the side lengths first. Okay. So in the diagram, we know PQT is similar to triangle RST, and the area of RST, so we know the area of the smaller one is 75 square meters. We want to find the area of the big one. So we want to find area of the big one, area of B. Okay. Okay, so if we go ratio big to small, we're finding area of big divided by area of small is going to be equal to, if we go big to small, they give us one side length. Its corresponding side length is 10. So we have corresponding side lengths. Okay, so we could equal it as 14 to 10, but since this is a square measure, these have to be squared. So 14 squared to 10 squared. Be careful, 14 squared is not 14 times 2. It's 14 times 14. So we're looking for the area of the big one. The area of the small one is 75, equals 14 squared, which is 196. 10 squared is 100. So now again, we means extremes it. Okay.
Ms. Baumeister would like everyone to know that there are extra flowers, pop, and candy in her room. Thank you.
Sorry about that interruption. So we're going to multiply the extremes, 100 times the area, and then multiply the means, the 75 times the 196, and those will be equal. 75 times 196, 14,700 equals 100A. Divide both sides by 100. A equals 70 divided by 100, 147, and square meters. Area is in square units. Hey, word of caution here, this always goose people up. Do not forget you need to square the ratio of the side lengths to get the area. Okay, you have to square those to get the area. Okay, we have one more example left, real quick. Example 6. Okay, decide whether GNMH and MLKH are similar. Explain the reasoning. So to determine whether they're similar, hey, you need to verify that all side lengths are proportional. All sides are proportional. Okay, so if we look at, we're looking at triangle GNMH. That triangle right there. So we know rectangle, right? We have 4 right angles. So if this side's 25, this one is. This side's 10, then this one is. And then we're looking at triangle MLNK. MLNKH. So what I'm going to do is I'm going to actually draw this triangle separately. So let's see, this would be MLKH. M to L is 4. Again, we have all right angles as well, so this side's 4. And then M to H is 10, so this side's 10. So basically, I'm looking for those proportions. Okay, so we would need to put G to N over M to L, so G to N. So basically, I'm looking, is G to N over M to L equal to N to M over L to K equal, again, I'm just M to H over K to H. And does that equal last? We're going to go H to G over H to M. Okay, so we put our sides in. So G to N, 10 over 4. Does that equal N to M, 25 over 10? I can tell right there. I can stop right at that point because 10 over 4, that simplifies to 5 over 2. But 25 over 10 simplifies, to 5 over 2. So, because I can tell then that M to H is going to be 10. K to H is 4. So that's also 5 over 2. And then H to G is 25. H to M is 10. So again, that's also 5 over 2. So if you notice, we have that constant ratio, 5 over 2, 5 over 2, 5 over 2. So yes, they are similar.